Alright, chemistry, this is your video lecture for chapter 7, section 3. We are going to start using those chemical formulas that we introduced in section 1. So after this lecture, I want you to be able to calculate the formula mass or molar mass of any given compound. And yes, those are different things. I want you to be able to use the molar mass that you just calculated to convert between mass in grams and the amount in moles of a chemical compound. All right, here we go, conversions again. Then calculate the number of molecules, formula units, or ions in a given molar amount of a chemical compound. And then lastly, calculate the percentage composition of a given chemical compound. Let's get started. We're going to start with molar mass. Formula mass. Now, before we look at what a formula mass is, I want to remind you of what the molar mass is. The molar mass of a compound is the mass of the atomic mass units of one molecule. Okay, take all of the units that make up that compound, take their masses in atomic mass units, add them together. That's going to be the molar mass. However, that's going to be in grams per mole. When we do this, when we talk about molar mass and we talk about grams per mole, in fact, anytime we use the unit moles, we're taking into consideration the number of atoms of each element that are in that compound, the number of molecules that are in that sample. Formula mass, however, is calculated the exact same way as molar mass, except it's measured in AMU, atomic mass units, instead of grams per mole. So that means that, yes, the number, numerically, they are the exact same. However, formula mass is measured in AMU, and molar mass is measured in grams per mole. Molar mass is on a much larger scale, much more useful for everyday chemical things. AMU, the formula mass, is incredibly small, not all that useful in everyday life. So let's see if we can remember how to do this. Calculate the formula mass, okay, again, of one molecule, formula mass of magnesium carbonate. Now, at this point in the course, you should recognize that that carbonate is a polyatomic ion. You need to look that up in your polyatomic ion sheet, and you'll be able to figure out that the atoms that we have in this compound are magnesium, carbon, and oxygen. However, I need to account for the fact that I have three oxygens in that carbonate. Okay, we have MgCO3. So when I go to set up my calculation to actually add these things together, I need to multiply the 16.00, again, that's the mass, the formula mass of oxygen. I need to multiply that by 3. And so I end up with 84.32 AMU. Again, I know I'm going to use AMU because this is asking for formula units. If I was doing a problem, answering a problem that asked for molar mass, I would use grams per mole. So keep that in mind. Speaking of molar mass, it's the mass of 1 mole of a pure substance. A mole is an amount. Okay, it's an amount of a substance. For example, when you say you have a dozen eggs, you have 12 eggs. It's another word. It's a little bit more useful for us when we talk about groups of eggs, because typically we buy so many at a time. It's much easier to talk in terms of 1 dozen or 2 dozen or 3 dozen in terms of 12, 24, 36. It's a little bit more convenient. In the same way, we use this term called the mole. Now, the number that the mole represents is a lot larger, but it's still an amount of a substance in that exact same way. So the mass of 1 mole of a pure substance is called its molar mass. For example, the molar mass of iron is 55.847 grams per mole. And again, I used grams per mole as the unit because this is molar mass. If I was asking for formula mass, I would say AMU. And where do I get this information? Where did I get the 55.847? The periodic table. All right, looks like my animation got a little bit messed up, so your little practice is going to be pretty darn easy. What is the molar mass of platinum? Again, look at the periodic table. Find platinum. The number in that box is 195.08. Now, again, there's not going to be a unit on the periodic table because it's up to you how you use that information. If you're looking for molar mass, you're going to slap the grams per mole on there. If you're using a formula mass, you're going to slap an AMU on there. And again, that number, we're getting that number from the periodic table. So molar mass will vary from particle to particle, okay, whether it's an individual atom or polyatomic, something large. It's going to depend on the particles that compose that compound. Now, if your element exists as a molecule, right, Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, 1 mole of these particles is going to contain 2 moles of the element of that atom. Because remember, bromine, we're not going to find pure bromine, a molecule of bromine in nature as just 1 bromine atom. That's not a molecule. These are diatomic molecules. It means it takes 2 atoms to make 1 molecule. So that's why I stress this mnemonic here, Brinkelhoff, so you can remember those elements that are going to be diatomic. It's very important. This will cost you points on a quiz or on a test if you do not commit this to memory. Again, Brinkelhoff makes this easy. So let's practice what this looks like. Determine the molar mass of oxygen molecules. Okay, so when I say a molecule of oxygen, that means O2 because it's Brinkelhoff. That O in there is oxygen. It takes 2 atoms of oxygen to make 1 molecule of oxygen. So I'll take the molar mass of oxygen, which is 16.00 grams per mole. Again, I'm talking about molar mass, so I'm using grams per mole. I know that it's diatomic, so I need to multiply that by 2. And so the molar mass of oxygen molecules is 32.00 grams per mole. Okay? And so what we really need to remember here is that the molar mass of oxygen, the molecular oxygen, or any of the other elements that are in Brinkelhoff is going to be twice the molar mass of its elemental form. So when we are calculating molar mass for compounds, here's a list. Follow this procedure. List your atoms. Make sure you know what's involved in that molecule, what's involved in that formula unit, and then identify how many atoms of each of that element is present. Okay, I have these types of elements. I have this many of those elements. Then I'm going to use the periodic table to identify the atomic masses of those elements. Now that I have that information, I'm going to multiply that information. I'm going to multiply how many atoms are present by their respective atomic masses. And lastly, add those up. You got yourself molar mass. All right, let's try this out. I'll walk you through the first 2. There are going to be 4 examples on this page. I'll walk you through the first 2. I'll have you guys try the last 2. Let's start with water, H2O. I'm going to calculate molar mass here. As you can see, my animations are a little out, so you can already see the units that we're going to be using are grams per mole. How do I know that? I asked you to calculate the molar mass. That's how. Molar mass, not formula mass. So I identify I have hydrogen. Okay, I have 2 of them. I'm going to multiply that by the mass I find on the periodic table. Now, different periodic tables are going to have different numbers of significant figures, so the periodic table that you guys are using in class isn't going to be quite this exact. I believe it has 1 fewer significant figures. Don't sweat that. Okay, don't sweat that. Different periodic tables use different numbers of significant figures. We're just using a little bit more here. So when I multiply those 2 numbers together, I get 2.0116. Leave that there. Now move on to oxygen, because I also have oxygen in this molecule. There's 1 of them. I'm going to multiply that by 15.99. Again, that's 15.99. Lastly, I'm going to add all these up. I got 18.006. So the molar mass of water is 18.006 grams per mole. Moving on to NaCl. I have 1 sodium atom coming in at 22.9 AMU, or grams per mole if you're looking at a mole of it. I have 1 atom or mole of chlorine coming in at 35.45. Again, just 1 of them, so I just bring that right over, add those together, and I get 58.35 grams per mole. Now, if I wanted to calculate the formula mass, I would actually use that exact same number, exact same procedure, exact same number, just instead of grams per mole, I'd use AMU. All right, guys, go ahead and press pause and try C6H12O6, which is glucose. Go ahead and press pause now. All right, let's see how we did. We have 6 carbon atoms coming in at 12.01, 72.06 altogether. We have 12 hydrogen atoms, each at 1.008, coming in at 12.096 altogether. And lastly, we have 6 oxygen atoms coming in at 15.99 each, for a total of 95.94. Add all those together, we have 180.096 grams per mole. Again, if we're going to use appropriate and significant figures, which I probably should have, not probably should have, that would just be 0.10. That would be the appropriate number of significant figures. My bad on that one. All right. Last one for you guys to try. K2O, that's potassium oxide. Go ahead and press pause and calculate the molar mass. Let's see how we did. We have 2 potassiums, each one coming in at 39.1 for a total of 78.2. I have 1 oxygen coming in at 15.99. Add all those together, we get 94.19 grams per mole. Again, that should be 94.2. Someone didn't go back and consider significant figures. That would be me if you were wondering. So looking at the mole, it is the reason that we have this thing called the mole is because it's more convenient to use this special counting unit when we have lots and lots of these particles, which if we're going to use anything that's useful for us on our macro scale, on our real life scale, we are going to be using huge quantities of particles. So moles end up being incredibly useful. A mole, as far as its definition, it's a unit that contains 6.022 times 10 to the 23rd objects. Anything. It's not reserved for chemical things. Now, it's most useful for chemical things, atoms, ions, molecules, formula units. Yeah, it's most useful for those. But you can use it for anything. You can use it for macro-sized desks. It's just that that's not going to be a very useful number because, notice, it's so large. It's times 10 to the 23rd. But in order to stay generic, because it's not always atoms, sometimes it's molecules, sometimes it's polyatomic ions, we use the term particles here most often. So 6.022 times 10 to the 23rd particles, because that's a very generic word that we can use for atoms or molecules. Again, we use this because of the very, very incredibly small size of the atoms and molecules and ions that we are going to be using. Now, this number, 6.022 times 10 to the 23rd particles being in 1 mole, again, that's the definition of a mole that you've already written down, you've already heard this year. We call that Avogadro's number. Okay, that number, 6.022 times 10 to the 23rd particles, that number is Avogadro's. And so we use this number very often. Quite often we don't actually say the entire number out. A lot of times we'll simply say Avogadro's number because it's easier to say. But when we look at the periodic table, the average atomic mass, okay, is listed in AMU. That's 1 atom. Okay, that's 1 atom. The weight of 1 mole of an element, okay, if we have 1 mole of a pure element, it's going to be that exact same number, but in grams per mole. Okay, this is going to be a large amount. Again, 6.022 times 10 to the 23rd particles. That's a huge number of things. This is going to be a lot larger than something that would be measured in AMU, because something measured in AMU is going to be on the scale of 1 atom, 1 ion, 1 molecule. Okay, it's going to be much, much smaller. And so what we'll need to know is that Avogadro's number provides a connecting relationship between molar masses and atomic masses, which we will use in this class quite often. So let's try some of these. How many molecules of bromine are present in 0.045 moles of bromine gas? Again, Brinkelhoff, remember that. So, given, we have 0.045 moles of Br2. And I know this is Br2 because bromine is a diatomic molecule. I remember that because of Brinkelhoff. So, we've been given moles of bromine. We need the number of molecules of bromine. And like we just saw on the last slide, what's going to get us there is Avogadro's number. We're going to use Avogadro's number as a conversion factor. And if you remember, we need a statement of equality before we can move on to actually create this conversion factor. And that statement of equality is 1 mole of Br2 is equal to 6.022 times 10 to the 23rd molecules of Br2. Because again, that's the definition of a mole. It's that many particles of whatever substance you're talking about. It's Avogadro's number. So now that we have that, I have two options for conversion factors to use now. They're very similar. However, I'm just flipping them numerator to denominator, denominator to numerator, based on what I've been given and what I'm going to. And if you remember from earlier in the year, I've been given moles of Br2. So in order to have that moles of Br2 cancel out, I want the unit moles of Br2 to be on the denominator of my conversion factor, because that's the only way I can cross cancel. I can get rid of those, and the only unit I will have left will be molecules of Br2, because again, that's what we need. That's what the question is moving us towards. So looking at these two options of conversion factors that I have identified that I want to use the first one there. I want to use this bad boy. Yeah, this is going to be my conversion factor. So when I set up the problem, I'm going to take what I've been given, the 0.045 moles of Br2, and multiply that by 6.022 times 10 to the 23rd molecules of Br2 over 1 mole of Br2. That way they can cancel, and all that's left for me to do is carry out some simple multiplication, and I end up with 2.7 times 10 to the 22nd moles of bromine. Again, one thing to look out for, this question says gas. Okay, in the question says moles of bromine gas. That's going to be one of the things that clues you into, like, hey, red flag. This is a molecule. Not just talking about bromine atoms here. We're talking about a bromine molecule. Gas is one of the things that's going to clue you in onto that. Any state of phase, something like solid or liquid, anything like that, it's going to clue you in. This is supposed to be a molecule, so heads up for those diatomic molecules in Brinkelhoff. Now, lastly, this is going to seem like it doesn't make a whole bunch of sense as we go through, but I'm really hoping you guys follow along with this slide. Use this slide for reference. It's going to help keep your head above water as you try to do this percent composition problem. You're going to see this. Calculate the percentage compositions of magnesium carbonate, again, MgCO3. Now, in a past slide, we already calculated that the formula mass of magnesium carbonate is 84.32 AMU. What I'm going to do here is I'm going to take that 84.32, the mass of the entire molecule, of the entire, well, it should be a formula unit, of the entire formula unit, and I'm going to divide the mass due to each individual atom, right? The mass due to magnesium, mass due to carbon, and then the mass due to oxygen. I'm going to divide each of those three numbers by 84.32. Multiply by 100, that'll give me a percent. You guys should remember this from basic math. That's what we're doing here. We're communicating percentages. So let's start off with magnesium. Magnesium, there's only one atom of magnesium in here, the 24.31. So we're going to take that magnesium mass, the 24.31, divided by the total mass, 84.32, multiply it by 100, we get 28.83%. Do the same thing for carbon. There's only one carbon atom, so that's 12.01 AMU. I'm going to divide that by the total mass, 84.32. Multiply it by 100, we get 14.24%. And lastly, now this is the only tricky part here, it's the total mass due to oxygen. Since there are 3 oxygens, we have to multiply that 16.00 by 3. And so I'm going to take 48.00 divided by 84.32 and multiply that by 100 to get 56.93. Now looking at this construction, I see that most of this compound is 56.93. That's the largest percentage here. That's oxygen. So oxygen makes up most of this compound. Now, lastly, I want to be able to double check that I'm correct here. And so I'm simply going to take all of the percentages, whether there's 2 percentages, 3 percentages, 4 percentages, right, depending on how many elements are in that molecule. And I'm just going to add them up. And they should equal 100. All right, guys, that's going to do it for this video lecture. I will see you next period.